Good afternoon. My name is Gang Xiao, and it's been a long tradition in our physics department. Once a year, we sponsor and schedule this distinguished lecture series called the Arthur Oney William Jr. Lecture. We have had more than 20 such lectures by physicists working on cutting edge of sciences. And today I welcome all of you to William's lectures given by Professor David Shoemaker of MIT. First, let me say a few words about Arthur William. He was actually a descendant of two prominent Rhode Island families, Roger William and the Oneys. His forebears include Stephen Oney, Secretary of State in the cabinet of Grover Cleveland. Arthur grew up in East Providence. He graduated from East Providence High School in the 1930s. He went to MIT on a scholarship after winning a nationwide science contest. Arthur graduated from MIT in 1934 and came back to Brown and worked with Professor Bruce Lindsay on the atomic wave function calculations. Afterwards, he was a professor of physics at the University of Maine for 3 years, and then came back as physics professor here for 30 years. He became the chair of the department in 1955, overseeing the expansion of the department from acoustics to solid-state physics and particle physics. Professor Williams was a distinguished physicist in the field of acoustics. He received the Pioneers of Underwater Acoustic Medal from the Acoustic Society of America in 1982, and today we continue to benefit from his legacy and generosity. With that, I'd like to ask Professor Rick Gateskill to introduce today's speaker.
Thank you. So, good afternoon, everybody. So I'm just here to introduce David Shoemaker, who's very kindly agreed to talk to us about what I think, and I hope many of you already understand, is probably one of the most exciting experimental sort of cosmology astrophysics experiments we have running right at the moment. It is seeing for the first time gravitational waves, and obviously he's going to spend quite some time telling us about that. I think another reason why you sort of want to pay attention to this story is because it does represent, the long road that often these amazing scientific breakthroughs are required to go through. I mean, and I hope I'm not going to repeat too much of what you're likely to tell us, but it's back in the 60s that Rainer Weiss, who David went on to work with, who is doing the experimental and proposing this idea of interferometry as a mechanism for what ultimately became the ability to detect over scales of, well, I think it's 4 kilometers, you're able to see less than a movement of less than 1/10,000th of the width of a proton. Not an atom, not the width of an atom, the width of the proton, the nucleus inside. And at the same time, the theoretical, the astrophysics, this idea that there would be a signal, as Kip Thorne at Caltech is really trying to figure out, what magnitude would these gravitational waves have. So, as I say, that's the 60s. Now. David was, lucky enough to work, directly with Ray Weiss, and at MIT, and he then had spells in both Germany and France. Where in France, I believe he got his PhD and a driving license, both fairly high-risk occupations. I've worked with a number of French physicists. God knows how I survived the driving part of it, actually. Anyway, but then David moved back to MIT. He's really, so when the late 90s comes around, again, as I'm sure we're going to hear, the phase Well, one of the things, again, you have to realize about LIGO is you go to the 90s, and although they managed to demonstrate some fairly significant progress in terms of building prototype instruments and what have you, you still, year after year after year, they are going to the funding agencies looking for approval, looking to get funding. It was quite a campaign, I believe, during that period. But by the time you get to late 90s, they're in this phase where they're actually going from the original LIGO, which didn't see anything, didn't have enough sensitivity, that you then have advanced LIGO, which late 99 was in white paper form, and then that led ultimately to approval of funding proposals and actual construction of the advanced LIGO, which is the instrument we're going to be hearing about, which took place from 2008 through to 2015. And then, of course, amazingly, having been finished, they turn it on and immediately signal, which is obviously a fantastic way to begin a story. And in that sense, you can say it was a hell of a road to travel to get all the way to 2015 to start getting signal. Already you're looking at 40 years of sort of plus of journey. But also, of course, we're right on the threshold now of doing a whole new style of astronomy, which is, well, it's fantastic to, right at this birth of this new field to hear from David. So without further ado, I really should hand over to you. Thank you so much for being here.
I hope it will be an interesting lecture for you all. I build instruments, and so that's really very much going to be the focus of what I'm going to talk to you about, and I hope it will lead you to have some intrigue for the fundamental physics of measurement that challenge us. I also say a little bit about astrophysics, but that's not going to really be the focus here. 100 years ago, roughly, Albert Einstein, our favorite patent officer, was looking at how to synchronize electrical systems across Europe. Commerce was starting to grow among the various different European nations. He also had a tendency to close his eyes and dream about falling in elevators and so forth and so on. It led him to be able to come up with both special relativity and then general relativity not so very long afterwards. He also made a prediction for gravitational waves as one of the consequences of his formulation of general relativity. He wrote a paper in 1916 that contained an error that said that there would be no gravitational energy transmitted through gravitational waves, so they couldn't be discovered. An anonymous reviewer gave him a review saying that he forgot something, and without ever apologizing, he then published a second paper in 1918, so just 100 years, which said, in fact, there would be gravitational waves. But he also made a calculation. We've looked through his notes to try and find out what he used as an example to conclude that it would be impossible to see gravitational waves. But I think by any technology that one could have imagined at the time that he came up with this theory, it was true. It would be a fool's errand to try and detect gravitational waves. So a little bit of time passed. Oops. Yeah, there we go. And by 1993, we'd had a number of decades of people trying to develop technologies that could be used to do this. The laser came along, meanwhile, and offered us opportunities for precision measurement of length and so forth and so on. And by the time 1993 arrived, we could propose to the National Science Foundation to establish observatories. I'll be telling you why they take this particular form. The proposal does state clearly that the initial detectors only had a chance of making detections, and it was probably going to be necessary to iterate on that. I have to say many times over, the National Science Foundation has been a wonderful partner for us in making this research happen. It's a great funding agency, and they deserve a lot of the credit. So this is the proposal cover art for what we sent in 1993. And then they sent us a bunch of money, and so we built it for real in about the same environment. Caltech and MIT built this together. We were partners in that. And this is the Hanford Observatory. So then, from 2000 to 2015, we went through a gestational period. Virgo, a French-Italian collaboration, also built an instrument. It's almost close enough to the Tower of Pisa to see it from the observatory. We did what we call commissioning, which is bringing the initial instruments to ones which were performing at the limit of sensitivity that we said they should. We observed for quite a number of years, and we saw no signals. We actually got some interesting upper limits out of it. We also learned a great deal about building these instruments and what not to do again. So in parallel, the LSC, LIGO Scientific Collaboration, and Virgo, we were working on R&D for second-generation detectors. We proposed ours in 2005. The project start was in 2008, completion in 2015, and I have to say this, I was the leader of that thing. I brought it in on budget, on time. I'm extraordinarily proud of that. The sensitivity target was 10 times better. It's important to realize we sense the amplitude of gravitational waves, not the power, and so the signal falls as 1 over r. If we can double the distance to which we see 8 times as many potential signals. A factor of 10 gives us an incredible leverage, some 10 to the 3 more sources in reach. That was our objective. Let me say a couple of words about gravitational waves. According to GR, gravitational waves propagate at the speed of light. They're emitted from rapidly accelerating non-symmetric mass distributions. And the result is a strain in space. It stretches and squeezes space. A very simple idea of how you build something like this is to take 2 massive objects and cause them to orbit around each other. A basic equation for strain looks something like this. A delta L over L is created. If I have a meter stick, it changes by a delta L according to the length of that meter stick. The amplitude falls as 1 over r, as I said. It is proportional to the source mass quadrupole moment, which is basically how asymmetric the thing is. The second derivative of that is acceleration. And then there's this fearsome factor of c to the 4th in the denominator. That's really what makes it hard to do this experiment, and it's reflective of the stiffness of space. Space-time does allow you to cause ripples to flow, but it's very, very stiff. If you make a number up for the strain due to this rotating dumbbell, well, it gets bigger if the mass is bigger. It gets bigger if the r is bigger, because that makes a bigger mass quadrupole. It gets bigger if you have a high frequency, and it's still got these terrible factors. So the number that falls out, if you say you want to see something at least once a year, then you probably have to have a sensitivity to strain of about 10 to the minus 21. Let's say a meter stick will change its length by 10 to the minus 21 meters when the signal goes by. You can only really expect to make measurable gravitational waves from the coherent bulk motion of matter on the order of stellar masses in the highly relativistic regime. Otherwise, the signal will just be too small to be accessible to any experimental techniques that we currently know about. What is that experimental technique? We use enhanced Michelson interferometers. Imagine you have a ring of free particles, and there's a gravitational wave that's passing into the plane of this projector screen. And it's a sinusoidal wave. It will distort space, making an ellipse with one major axis and then the other major axis with a frequency that corresponds to that gravitational wave. Ray Weiss's intuition, he wasn't the only person to think of this. Good ideas come to many people. He was the first person to think through what was hard about doing it and doing it right, is to place a Michelson interferometer on that ring of free particles. It's ideally suited for measuring the difference of L1 minus L2 by looking at the difference of phase of arrival at this beam splitter. Here's a somewhat larger drawing, and you imagine you shorten this arm and you lengthen this arm. It will change the return phase from these 2 arms and cause a fluctuation in light at this output detector. So it acts as a transducer, turning gravitational waves into a photocurrent. It's a really beautiful idea when viewed so simply. Now, our arms are short compared to our gravitational wave wavelengths. There are a bunch of practical constraints that lead us to gravitational frequencies on the order of audio signals, 10 hertz, 100 hertz, a kilohertz. And with the speed of light, you can calculate that that leads to hundreds and hundreds of kilometers of wavelength. So the longer we can make our arms, the larger the signal. That arm length is limited by taxpayer noise, by the way. It's one of the noise sources with which we deal. So I said that if you want to see a signal sort of once every year or more frequently, you have to have a sensitivity of 10 to the minus 21. And to give you a sense of that, that's a delta L over L. Protons for me are not very physically accessible. To me, a little bit better is the distance to Alpha Centauri, it's about 4 light years or so. Thickness of a human hair, it's about 10 microns. We can resolve fluctuations in that distance by the thickness of a human hair, the distance to Alpha Centauri. And when a gravitational wave passes, in fact, it changes the distance between us and Alpha Centauri by the thickness of a human hair. And that's what we can sense. That's what we must be able to sense to do this experiment. The bottom line is that we need to be able to detect effectively fluctuations of this length on the order of 10 to the minus 18 meters in tens of milliseconds. So this is the sort of sketch of an interferometer. I already snuck in 2 input mirrors here, which I didn't talk about. They store the light for a longer time in the arms, gives you more photons to interact with, a somewhat better sensitivity. Then you say you have to fit that into a real optical schematic, and you have to come up with mirrors to couple light in and couple light out. Then you have to fit it into a vacuum system, because if the light that we use as sensing sees a fluctuation in the density of air along the way, it's like shimmering light over a highway. It would completely ruin the measurement. And then you have to fit all of the components on. It's an incredibly complicated thing. I have a really neat animation here that's going to lead you through the optical system, and I'll try to voice over my way through it. This is an actual physical view of the Hanford Observatory up in Washington State. And now we move over into CAD/CAM space. And we're going to rip the roof off of this building and look inside at the vacuum system. So these pipes are about 1.5 meters in diameter. And we're going to run down to the end where the laser in this Michelson interferometer sits. The animator cheated, and he doesn't actually show us the laser, just has it start spontaneously at this point here. And now the light beam falls through a pattern of mirrors. This first optical system, it's a triangular cavity made up of 3 mirrors, tick, tick, and tick, and it acts as a frequency reference and also as a beam stabilization device. We transmit the light through that very stable cavity. Then we fall on a couple of focusing mirrors that take us from the kinds of beams you usually see at the output of a laser to the kind of beam that's matched to a 4-kilometer wave long arm. It now falls on that beam splitter, which is about a 40-centimeter plate of very, very fine glass. And through the first input mirror of this arm cavity, which increases the laser power, this animator chose to pause for a moment here and show us how the light intensity is built up by about a factor of several hundred by the light falling back and forth on resonance within this longitudinal Fabry-Perot cavity, which increases our sensitivity. Now what we're going to do is take a path down the arm as though we were a photon and take a look at the mirror at the far end of this interferometer. And there we see, housed in a rather large vacuum system, the object itself. This is the mirror, which is isolated very, very well from the outside world and moves to the gravitational wave. And then back to the beam splitter again, where we'll see the beams recombine. I may have just turned the volume all the way down with this button. I wonder how I turn it back all the way up again. And now the output beam from this interferometer comes. We actually work the interferometer to dark fringe. I'm sure you know an interferometer has a kind of cosinusoidal output on a function of path length difference. We work at the dark fringe, but here it's shown rather bright. Goes through a couple more filter cavities, and then it falls on a photodiode. This is the thing which converts light intensity into fluctuations in photocurrent. Now, when a gravitational wave passes, this would have to be a rather strong gravitational wave, a little bit stronger than 10 to the minus 21, we see at the output of the interferometer the fluctuations in intensity. And here the animator chose to have us move back and forth between the minimum in the output of the interferometer. In fact, we sit a little bit off to the side and move a tiny fraction of a wavelength around there. But in that photodetector, then, we see a time trace, the electrical current versus time, maps out the strain in space as a function of time. And if we're lucky, there's a gravitational wave that passes. So I'm going to tell you a lot more about that measurement process, because it's the stuff that I really love. We're going to see a number of these plots. This is strain. This is the delta L over L, measured in a 1 hertz interval, integration time. And here's frequency, 10 hertz, 100 hertz, kilohertz. So these are frequencies that you could hear with your ear if your ear were that sensitive to strain in space. And what we see here is the sensitivity curve that we had for our first observing run with the new interferometers. I'm sorry, with the first generation of interferometers. And I'm going to show you a number of things that we did to reach the better sensitivity that we have with advanced LIGO. And the first one is up in this, what we call our high frequency region. There's a much reduced shot noise level. What is shot noise? The photons fall on our photodetector one by one, following Poisson statistics. And I think you probably know now that the fluctuations, the fractional fluctuations in Poisson statistics go with the square root of the number of objects that are following, the square root of n statistics. It's interesting to note that Einstein was the first person who brought this fact to our attention. And so we can note that the fringe resolution, our ability to split this fringe, increases at the square root of the power that falls on our photodetector here. And here we see the strain limit goes as 1 over L, as I promised you. And then in the square root sign, there's a power in the denominator. So that's one half of the story here. The other half of the story is that as you turn the power up to get better and better sensitivity here, you actually start to shake the test masses. The momentum transferred by the photons to these 40 kilogram pieces of silica that we saw at the far end of the tube there, it causes them to shake. And it has a spectral density of 1 over f squared because your mass has got inertia and it doesn't want to move. But that means that the strain limit due to that effect of the radiation pressure noise falls as 1 over m f squared, m omega squared, if you will. And then now this gets worse with higher power. So you can obviously see you can solve these two equations to find this frequency of best sensitivity, happens to be right here, but you have something which is called the standard quantum limit. And these advanced LIGO detectors actually operate at the standard quantum limit. The next thing that limits our sensitivity is the thermal noise. This is effectively Brownian motion. There's kT of energy per mechanical mode. This is a mechanical object. It's sitting at room temperature, 300 degrees, and it's shaking. Its internal modes are being excited by the fact that it's in equilibrium with its environment. Once again, it was Einstein who taught us about thermal noise. In a simple harmonic oscillator, the RMS motion just goes as the square root of kT, where kT is the Boltzmann constant over some kind of characteristic spring for the system. But it turns out that's distributed in frequency according to the fluctuation dissipation theorem. I pressed this button again. How can I get the sound to come on again when the time comes, I wonder? And the consequence is that you have a spectrum of excitation, which is, it falls as a function of frequency, and it gets smaller and smaller as you make lower and lower loss mechanical systems. So the objective is to make a mechanical system with as low loss as possible, and we moved from a rather dumb sort of wire-suspended system in initial LIGO to this very fancy monolithic fused silica system to reduce the thermal noise at lower frequencies. Curiously, the thing that's lossiest in the system is the tens of microns of reflective coating that's on the surface of the mirrors, because that's much lossier than the bulk object of this test mass. And as a consequence, we have to work very hard to get the noise down in this critical middle region. And to get that to be better is material science. That's really complicated science. It's not like simple stuff like quantum measurements. And so as a consequence, we are working hard with a bunch of people who understand coatings better than we do to try and make better coatings yet than the ones we have. But we already improved them for advanced LIGO. And then there's the thing which you might have thought of first, and that is seismic noise. There's this constant motion around the instrument. You have to isolate this object here, this test mass, from being influenced by these stray forces. And that involves, in our case, first using multiple pendulums. You know, if you have a pendulum and you move it very, very slowly, the test mass will simply follow that point of suspension. If you move it at the resonance, then there will be a very high level of excitation, probably. And then if you move it quickly, the mass will sit relatively still. That last fact is what we use to do several of the layers of isolation of our masses. But we also have highly active systems where we have a seismometer that's measuring motion, developing a feedback signal to a motor, and holding the table still in inertial space. With multiple layers of that kind of isolation, 3 layers each of 6 degrees of freedom, we can move the lower frequency limit down in performance from about 40, 50 hertz as it was for initial LIGO down to about 10 hertz for advanced LIGO. And that allows us to observe a lot of astrophysical systems for a much longer time, do more astrophysics.
What's causing it to rise so dramatically?
It turns out that the parent spectrum for seismic noise is typically 1 over f cubed or 1 over f to the 4th. And then there are a bunch of other systems in series with that have sort of 1 over f squared characteristics. So you end up with sort of an f to the n, where n is 10 or 15 by the time you get to the actual instrument. So there's an ultimate limit on the lowest.
And the fact that it kicks in at some 10 hertz, is that just serendipity? Well, I don't know, serendipity is the wrong word, but I mean, the fact that there was sort of space there, is there a way of understanding why 10 hertz is
It's a practical matter. It's actually the thermal noise of the reference masses in the seismometers that determines the lowest frequency to which you can do a proper job of isolation. But my next slide will tell you why there's no point in going any further, which is that there's a limit on the Earth due to the Newtonian background. What is the Newtonian background? Seismic waves, either body waves where there's a compressional wave running along the surface, or Rayleigh waves, which look a little bit more like ocean waves, both end up making a dynamic, time-varying change in the density of the matter around our test masses, which I've described in this pretty drawing here, actually, Jan Harms has. And our test mass is attracted to dense material, at least in the Newtonian vision of gravitation. If you put a lead ball here, the mass is going to be pulled toward that lead ball. And because that lead ball is moving all over the place, our test mass is moving in response to these seismic waves. We cannot filter that out. That's a fundamental interaction between the mass, it's actually deforming space-time, near our test masses. And that gives us a noise level on the Earth's surface, just due to the practical level of excitation, which makes it useless to work on getting direct seismic coupling lower than 10 hertz. So we expect to be limited by this noise source around 10 hertz or so, because we're on the surface of the Earth. We would love to be limited by only this noise source. I'll give you a picture of what we are limited by in just a minute. If you want to go lower in frequency, you have to go underground, where there's less seismic excitation. And if you want to go really lower in frequency, then go to space. Get away from this noisy Earth. Well, I think I have one slide on that, too. So I've given you a litany of the basic noise sources that limit our measurement. Here, once again, strain versus frequency. You'll recognize all these various different terms that I've recounted. This is the sensitivity of the instrument that we were able to achieve for the first couple of science runs. We just started the third one today, which with a slightly better sensitivity. And what you can see is that the sum of these naive noise sources is lower than what we achieved. And to get from one to the other involves a lot of commissioning, a lot of working through very practical problems. What's fun is to look at the next slide. This is what we actually look at when we're trying to commission these instruments. There are all kinds of additional noise sources that we have to deal with, having to do with electronics, noise in systems, coupling from angular motion to longitudinal motion, so forth and so on. And they all pile up at low frequencies because of various different couplings to physical ground motion. However, we do get the kind of resolution that's needed to make gravitational wave detections already, even though we have more work to do. I think that's kind of fun to see is moving from initial LIGO to the first runs of advanced LIGO, we made about a factor of 3 improvement in the high frequency regime. And again, coming back to that cube, that means that there's about 27 times more objects which are within our reach, raising our probability of detection by a factor of 27. What's really striking is the improvement that we made at low frequencies, about a factor of 100 improvement. You can cube that to see how many more sources at low frequencies were available to us. We really did make a qualitative change in our ability to make gravitational wave detections by moving from the initial instruments to the advanced instruments. So with that, we were able to make our first detection. It did happen. It actually happened. We were doing an engineering run for the week before our observation run, and our first event happened during the engineering run, even before the observing run started. What we see here is, again, strain in space, and the numbers are about the ones I promised to you, 10 to the minus 21, versus time, where 2 tick marks is 1/10 of a second. And there are 2 traces here. One of them is for our Livingston Observatory, L1, and that's in blue. And the other one is H1, which is the one at Hanford. And it's shifted in time because the signal didn't arrive at the 2 observatories at the same time. The signal wasn't directly overhead between the 2, but off to the side. So it first arrives here and then here. Could be anywhere in this circle of confusion, by the way. And it's inverted because the 2 instruments are actually like this and not like this on the Earth's surface. So you have to invert a sign. But we saw this beautiful signal, which is visible without any fancy sensitivity you don't have to assume a model for gravitational waves or anything. This is high pass and low pass, like adjusting the treble and bass control on your hi-fi. And the signal was visible in the photocurrent at the output of the instrument. It surprised us, I'll tell you that. A thing that I really want to stress, how many people here know what a strip chart recorder is? Yeah, okay, 10% or so. It's a thing, you have paper that's coming out, it's being drawn by a motor, and then you've got red ink that gets all over your hands when you try to refill it, and it's got a galvanometer needle, and it swings across the paper. That's the kind of thing. We measure h of t in this instrument, which gives it an enormous power. You should know about these beautiful measurements that were made of the decay of an orbit of 2 pulsars, made by Taylor Holtz-Weisberg, and they could see that that orbit was speeding up and the 2 objects were approaching each other, and the loss of energy that was implied was exactly what was predicted by Einstein for gravitational radiation. They won the Nobel Prize and they deserved it. And that was the best confirmation of the first deviation from Newtonian law. The thing that is special about LIGO is it actually measures in real time the stretches and strains in space. So you get the instantaneous amplitude rather than the time average power, and it has much richer information. You can read things into these signatures that you couldn't get from that other approach. A second detection that I want to highlight happened, and I'm going to stress this date, it was on the 14th of August. Our colleagues in Italy had just started to observe with their instrument 2 weeks before, and we were able to see an event in all three of these instruments. This is the signal-to-noise ratio as a function of time. These are spectrograms. These are ways that we really like to look at our signal. This is the sound, this is the phone. This is the curve of the increase in frequency as these two objects approach each other and then coalesce into a single one. This is a superposed on the actual signal is the best fit model for a given source. And you can see that it's appearing very strongly in the two LIGO instruments, somewhat more weakly in Virgo, but visibly. And this was the first time that we'd had these three instruments working together and allowed us to do triangulation. You know, I said with two instruments, you have a confusion circle about where the source could be. When you add a third instrument, suddenly you have a patch on the sky. And that's a really great thing for talking to astronomers. Well, a wonderful thing, I have another slide on this. So LIGO can make this sort of limitation in the sky with two detectors, but when you add the third detector, you narrow quite considerably the range of things you can see. Yes, please?
How come there's a factor of 2 difference between the Livingston and Hanford signal-to-noise ratios?
It's just a practical matter of the commissioning. Which one had we gotten the noise down more in? They're nominally identical detectors, but they end up behaving differently. The environment is different, but you know, just stuff happens. Mirrors can be dirty, that kind of thing.
How stable the temperature needs to be?
Say again?
How stable the temperature in the chamber needs to be?
Well, the chambers are the largest ultra-high vacuum system in the world, and so it doesn't really matter how stable the temperature is inside the tubes and so forth. The temperature does influence mechanical stability, but we have servo controls that hold things.
Relative distance.
The mirrors are hanging freely. It doesn't matter if the vacuum system moves around. Servo control systems hold the masses continually to be at exactly the right length. And then we look for deviations in that length. Okay, good. And so we were able to, with these three detectors and this first detection, reduce the uncertainty in position, but also in volume. We measured distance, and that's a really useful thing for astronomers as well. So that was on the 14th of August. An amazing thing happened on the 17th of August. I mean, I want to describe this to you. I hope there's a button here which says turn off sound, but I don't want to turn it off. I want to turn it on. I don't know if my technical helpers here can tell me how to turn the sound back up again. Let me see if, let me make sure it's, actually, it may even be up because it's DVI rather than, so when I press on this button here, it shows on the screen a loudspeaker with an X through it. So let me tell you what this is about. This is going to be a time trace, and then there are three different instruments here, and these are each spectrograms, very much like these short spectrograms that I showed you. And when we play this, I hope it will come out, otherwise I'll hold my lavalier microphone next to the loudspeaker. You'll be able to discern. You think it will work? I'll make it go and we'll see what happens. You'll be able to hear in the loudspeakers the photocurrent in the detector here amplified and played back. And you'll be able to hear the fluctuations in current that have to do with the in-spiral of this test mass. That's the background noise of the instrument. It's a mixture of quantum noise, thermal noise, a little bit of seismic noise. And the detector which was working best at that time was Livingston. And so you'll start to see the curve of the spectrogram here starting to trend up in frequency as these two neutron stars are spinning around each other. They're passing through, I don't know, 50 hertz, 100 hertz or so. Now, if you listen carefully, I hope you heard in there the sound of these two neutron stars spinning around each other as fast as the Waring blender in your kitchen and causing this wonderful curve. And it's visible in Hanford and in Livingston as two detectors. You might ask yourself, why doesn't it show up in Virgo? The antenna pattern for a single detector looks like a peanut. Here is a sketch of the two arms of the detector. If the gravitational wave comes from above or from below, it can excite maximally the difference of x minus y, okay? If it comes along one arm, then it has, because the forces are all perpendicular to the direction of propagation of the wave, it has no influence on this arm at all, but it still has influence on this arm. So there the antenna pattern's down by a factor of 2. If it comes in at 45 degrees, it doesn't excite either one of the arms. GW 170817 came in along the vertex of the Virgo detector, which is a really cute thing. Now, it's important to stress, it did no harm for localization. If you know that the detector is working and you see no signal, it tells you a lot about where the signal's coming from. Because we'd had that triple detection 3 days earlier, we knew Virgo was working. It was so cool. So the other thing that happened with this detection was that there was a gamma ray burst seen in Fermi and in integral, which was 1.74 seconds, the initial peak, after the end of our signal. And so the first question is, maybe that was just chance or something. But if you look at the position where Fermi saw its signal and the position where LIGO Virgo saw its signal, the probability of that taking place by chance is greater than 5 sigma. So it's a gold-plated coincidence. One of the very first things you can say, I told you earlier, gravitational waves travel at the speed of light according to Einstein. Well, Einstein was proved not incorrect once again. We can say that over a period of 140 million years, this object is 140 million light years away, the difference in arrival time between photons and gravitons, which follow the same not simple path through space-time, right? There's all kinds of minor gravitational lensing along the way. They're zooming along together. They arrive within 1.74 seconds. That's apart in 10 to the 15, which is a nice little fact. Next nice little fact that comes from this already mini multi-messenger measurement is that some binary neutron star mergers are progenitors of short gamma ray bursts, which had been theorized. Everybody thought it was likely, or so forth. But there it is. It's plain as I don't know, plain as something. Let me talk to you about the time evolution, though, of what we did with astronomers. The first signal that actually was perceived was from Fermi and integral. Even though it arrived 1.7 seconds later, they had faster electronics for identifying a signal. And then the two LIGO detectors were able to chime in and made their usual rather uncertain measurement of where things were in sky, because they're just two detectors involved with that antenna pattern. You add in Virgo, and it shrinks way down, not only in angular aspect, but also in distance. We sent those coordinates to the astronomers where light time was falling in Chile. And about an hour after nightfall in Chile, the first telescopes were able to identify GC 4993. And as I'll show you on a picture, I think on the next slide, there was a new spot of light there. A star was born. And that was the result of this binary neutron star merger. Whoops. Yeah, okay, no, though I don't have a photograph of it. So, but it was really quite impressive. You could see it with optical telescopes. So already we can say a number of things. We can give the sum of the neutron star masses very accurately. It turns out there's a degeneracy having to do with the angle at which you observe this binary system and the masses, which means that you can be you have to have some uncertainty in the individual masses of the two. But however, you can say that they're well within the ranges of what's expected for binary neutron stars. There are a number of other things that we could learn. Relatively little radiated energy compared with black holes. But it was a beautiful measurement that was consistent with Einstein's theories. We could start to see something about the neutron star equation of state. We'd have the habit of looking at binary black holes, which give really a very perfect and simple chirping sinusoid until the two horizons merge, and then you get the ring down of a final black hole, which I've not yet observed. But in the case of neutron stars, you actually start to slosh material around. It's a much messier, uglier system. And what we were able to see is to start to see a deviation from a simple point-like mass in spiral. And from that, we could make a plot of, well, these are effectively stiffness measures of the two different objects. And we could say that it was a more compact system than some of the models that existed. So we've already started to put some limits on the equation of state of the nuclear matter in neutron stars. It's a tough measurement for us. It happens at high frequencies, where I show that curve that's rising. That is to say, we're losing our sensitivity. And the coalescence happens up here in the high frequency regime. It's a tough call for us to make much better measurements. We need better instruments to do that. We were also able to make a first measurement that involved gravitational waves, the Hubble constant. We can give the distance to the object pretty accurately by assuming that general relativity is right, and that seems to have been confirmed by our black hole measurements. And with that, we can add a new ingredient that was otherwise dependent upon linked measurements and make an estimate of the Hubble constant. Well, you may know this plot well. There is the Planck estimate for the value of Hubble constant, and there is the one that's based on supernova, shoes, and they're actually in more and more tension as time goes forward as being disjoint. And so it really looks like there might be some physics behind that. So far, our result, standalone, is very broad, and it's about centered between the two. We would love to be able to help answer the question as to whether or not there's some real physics there. It'll take a couple of hundred more measurements. More generally, there was this multi-messenger bonanza that happened as a result of GW 1708-17. In addition to gravitational waves, there's visible infrared light, there were radio waves, there are X-rays and gamma rays. We sought neutrinos, but none were seen, which may be valuable information for some. At any rate, it was viewed by over 100 detectors. There was worldwide engagement. We published a paper with 3,000 authors. And that was about 1,000 gravitational wave physicists, about 2,000 observing astronomers. And I think it's something like a third of all of the observing astronomers in the world who joined on that paper. That's just amazing. And I just did a search the other day. There are 1,600 papers in the MIT libraries that contain the string GW 1708-17. It was a very rich event for a great number of observers. This is a summary of what we've been able to see so far, which is kind of cute. It's a series of these spectrograms along with the best fit waveform and then the actual waveform, which is a little bit hard to see in this lighting, for all of our 10 black holes, which have been published so far, plus the binary neutron star. I think it's a really nice way of seeing that there's a real zoo that's being formed. Here's another way of looking at that same thing. Each one of these blue pairs here are two progenitor black holes leading to a final black hole. There are a series of black holes that were identified through electromagnetic means. We've just about doubled the number of black holes with the few measurements that we've made to date. You can also look down here. There are many, many neutron stars that have been observed in radio. They're good radio beacons. Our two little neutron stars are here, sort of average beasts that made some new particle or object, almost certainly a binary black hole given its mass. And so this is a kind of a summary of what we've been able to do so far with the first two observing ones.
What's the y-axis?
Nothing. It's enough space to display all of our toys.
Sorry, the x-axis, the y-axis.
Oh, I'm sorry. The y-axis is in mass, in solar masses. So, for instance, you've got a 20 plus a 35 makes a sort of 65 minus a couple of solar masses for the radiated energy and gravitational waves. So far we've seen coalescing binary systems by the tens. There are a variety of other things that we continue to look for and are eagerly awaiting. Bursts of various different kinds. A supernova would be a fantastic thing if it's sufficiently asymmetric. To have that I double dot show up, you need to have asymmetry in the system. It would probably have to be in our local galaxy. There are continuous sources. Neutron stars spin and are very, very good timekeepers. But if there's an asymmetry, a physical asymmetry, it will radiate gravitational waves. And that should cause it to slow down as well as emit a sinusoidal gravitational wave. And then the sum of all of these different things going off at the same time would make some kind of radio static that we can listen to. And there is certainly, at some very low level, also the cosmic gravitational wave background, which is being sought also in the cosmic microwave background through looking at the polarization. It's very unlikely that we'll be able to detect this directly with any of the instruments which are currently underway, but maybe in the future. All of this work is done with the LIGO scientific collaboration and the Virgo collaboration. I've got this map here actually represents just the dots of the LIGO scientific collaboration. Virgo adds a handful of dots over here in Europe. There are about 1,600 members between the two collaborations, 120 institutions, 30 countries. And a thing that I've noted to a couple of persons here is the complete absence here in Africa, and we have to do something about that. So what does the future hold for us? This is our planned observing timeline. Down here we have years. You are here. LIGO Virgo. Kagra is a Japanese gravitational wave antenna that's just in the process of being completed and hopes to join our observing run soon. LIGO India is something which we expect to not be operational until 2025 or so. Do we know what's making that nice sound? Okay, good. A thing to note is our O3 observing run started this morning at 9 a.m. with instruments that are a little bit better than the previous ones. I think I'll say something about the rates that we expect. And we'll be observing with LIGO and Virgo as before. No competition, all collaboration. And we're looking forward to Kagra joining us. We'll then make a few more minor changes in the improvement of the performance of the system to make a further measurement. And you have to remember to cube the ratio of these two numbers if you want to know the kind of rate increment that we'll have as we go from measurement to measurement. We have then now just recently received funding to make improvements to our instruments, incremental improvements, we would say, but ones that will bring us up by something like a factor of 2 or 2.5 from what we'll be doing starting today. You can cube 2.5 and get the notion that we'll have sort of 10 times as many events by that time out to 2026. Yes, right. So 1 year O3 started today at 15 UTC, which is 9 a.m. here. 1.6 times the sensitivity, so about 4 times the rate. One of the important things about it is that we're giving public triggers. I'll say more about that on the next page. And what does that mean in terms of rates? We expect that we could have as much as, we're at the upper limit of what's practical. No, it's what's expected. 1 binary black hole per week and maybe 1 binary neutron star per month. So there'll be lots more objects to lay out on that graph. This O3 observing run, in 01 and 02, we had memoranda of understanding with observing groups, but we want to move away from a closed system into a more open system, so we'll have open public alerts. Anybody who's interested, amateurs or professionals, can receive GCN, galactic notices, which will let them know where we saw something and when we saw it. The timeline for that, we've also worked very, very hard on getting our alerts out more quickly. I noted to you that Swift and Fermi were able to get their signals to the world within, I don't know, it was a minute or so of the actual event taking place. It took us about 6 minutes, so we've been driving that down. By 1 minute, we want to be able to send out a preliminary alert so that telescopes can start to slew and see the very beginnings of the evolution of new objects, and then we'll refine the information as time goes forward. Here's what the overall map of detectors looks like on the surface of the Earth. We have the 2 instruments, LIGO instruments. We have advanced Virgo, which is already observing with us. There's the Japanese Kagra detector that I mentioned that we hope will come online in late 2019 or early 2020. We hope it will join our current observing run. And then LIGO India is an interesting one. We built 3 detectors when we built our 2 for LIGO, and we put 1 in storage and started looking for a good place to put the 3rd one. And it looks like a great place is going to be India. The Indian government is currently constructing, they just finished the procurement of all of the land and the contracts for the vacuum enclosure and the concrete and the buildings. And the objective is to have this instrument observing with the rest of the world by 2025. And what will that mean? Why is that interesting? The run that we just started has this as a sky map. The size of the ellipse tells you how uncertain our estimate would be for the position of a source that would happen to lie there. We have about 1 signal per week, and about 20% of the sky is in 20 square degree boxes. When we have 5 detectors with India and Japan, then 60% of the sources would be in 10 square degrees, which makes a really big difference for giving pointing information to observers. And you can see how the map is completely transformed to one where we can really give pinpoint information everywhere. We're in the middle of making this A+ upgrade, which is what brings us from that sort of 175 reach to sort of 330 reach over at the right-hand edge of my timeline. It's a rough doubling of reach. And so we will move into a regime where we have, there could be as many as 10 binary black hole detections per day, and also significant increases in these others, and then probably more and different kinds of objects will come into our zoo. We plan to be observing by 2024, and we think we can hold to that schedule. It's now difficult for us to turn our machines off. The astronomers all ask us, where are the data? Where are the data? Then we have bigger, grander plans to move beyond what one can do with a 4-kilometer baseline. I said the longer you make it, the more sensitive it is. If you make the system move from 4 kilometers to 40 kilometers, you increase the signal size by a factor of 10. But most of the other noise sources do not scale to increase. In fact, some of them actually even go down on that longer baseline. And so it's a really good thing from science perspective to make the thing 10 times longer. From the standpoint of a funding perspective, it's a really bad thing to make it 10 times longer. It only would be something that would be merited if we can show that this field has a long-term promise for a very broad scientific community. There are all of it, I just said all of this. So we have two concepts. There's one in the US, which is to make the system 40 kilometers long instead of 4 kilometers long, to build it on the surface and to continue to focus on the same frequency range. In Europe, there's something called the Einstein telescope. They have a notion of putting the instrument underground, and this helps with reducing seismic noise and also that Newtonian noise that I mentioned, because the seismic noise is physically smaller. The compression of the Earth is smaller underground. They have the notion of making a triangular system, which allows you to resolve the two 45-degree separated polarizations of gravitational waves in a single location. And also allows you to build it in Europe, where every square meter of the surface is doing something useful for mankind, or mankind is making an exploitation of the surface of the Earth, if you prefer. At any rate, it's a notion which is compatible with Europe in a way that this Cosmic Explorer in the US, they put it on the Bonneville Salt Flats and no one would notice. There's another way of looking at the capability of reach for the gravitational wave antennas that we've been talking about. This is the redshift to which you can reach. This is 1, 10, 100. This is the mass of the objects involved, 10 solar masses, 100 solar masses, 1,000 solar masses. The current instruments are these advanced LIGO and so forth and so on. They can see out to a redshift of a couple and are focused on these 100 solar mass objects. These much longer systems, ET and CE are their nicknames, can see out in principle to redshifts of almost 100. That is to say, they can see the entire universe. And at least in this mass range, they would see all of the collapsing objects, binary black holes of a reasonable mass, some tens of solar masses, in the entire universe. And you could map out the history of the universe in that way, a little bit like 21 centimeter cosmology. So when could this new wave of ground instruments come into play? We've had a couple of examples now. It looks like it takes about 15 years to get from hopes to something that actually functions. We could imagine in the 2030s, if we can move along reasonably smartly. We would, of course, partner with a variety of electromagnetic observatories that we expect to be in operation at that time. The worldwide community is working together, as they have on the current observations, also in the planning for the future. And there's a thing called the Gravitational-wave International Committee, which is coordinating the activities for building of really good airtight science objectives for these instruments. We've just submitted the astrodecadal review. But the crucial thing for these endeavors is to make sure that there's a broad enough community that thinks these are useful, so that they say, okay, instead of building another $1.5 billion telescope on top of some mountain, we will recommend that those funds be given to build a bigger gravitational wave antenna. Things like GW170817 help a lot in proving the worth of this new field. I think many of us in our field were astonished at how well that worked out. I hope we can do a few more of those. Now, there's a broad spectrum of gravitational wave sources. There's the cosmic microwave background, which could be read to measure a primordial gravitational background. There's pulsar timing, where you use the timing of the various different pulsars in space as a way of seeing whether or not a gravitational wave is destroyed in space. I spent a lot of time talking about ground-based interferometers. You can also put things into space. As I said, if you want quiet, that's a good place to go. So there's a project called LISA. It involves not 5-kilometer arms, but 2.5 million kilometer long arms. And it moves the best sensitivity down to kind of 1/100th of a hertz or so. There are a bunch of scaling laws I won't go into here. Unless you look at kind of million solar mass objects instead of 10 and 100 solar mass objects. You slave the shield satellites around the test masses so they're not buffeted by solar wind and the like. The orbit scans the sky. You have this triangular kind of system which pinwheels around the sun, chasing the Earth, and the telemetry is between those two there. And it looks like the launch is going to be in the early 2030s. It's something that's on the ESA timeline, and they have not canceled a mission yet. The kinds of astrophysics you can do with it, I won't spend any time on this, but just note that they see in spirals too that take a path like this through time, frequency, space. About some months before the final coalescence, they would start to see a signal, and they would watch it over days and hours of cycle times, and finally the coalescence would take place maybe at a hertz or something like that, with very high signal-to-noise ratios. You could do a whole bunch of really exciting GR with it, as well as map out more of the way that mass is distributed throughout the universe. So with that, I draw to a close. This is just the beginning of a new field. We've got new instruments, new discoveries. There are synergies between our gravitational wave instruments and the electromagnetic spectrum. We think it's going to be a great contributor to the general world of astronomy and astrophysics over the coming decades. Thank you.
Thank you. So questions, please.
And microphones are good, or you shout really, really loud. Yeah, okay.
Put your hand up if you would like to ask a question so we can get the microphone to you. Don't be shy, as they say. There we go.
I don't really need it, but okay, I'll use it. There's a question about the supermassive black holes. I did not quite catch the distinction between gravitational waves from them and from ordinary black holes.
There are some differences. The most spectacular one, besides simply the amount of mass, is the fact that they're surrounded by matter. And that matter plays a very important role in the way the two come together. And that, I mean, there have been actually some concerns about the final parsec. Do these things actually get up to relativistic velocities so that they radiate successfully before their interaction of their matter gums things up in such a way that you don't get a signal? We hope that it is the case that we get gravitational wave signals, and in that case, by looking at the details of that coalescence, we can read information out about that matter. One other thing that we hope to do with the supermassive black holes and the fact that they've got other objects near them is to map out space-time. The notion is that you take a lightweight black hole of 100 or 1,000 or even 10,000 solar masses, and you use it as a test particle swinging around this 10 to the 8th, 10 to the 9th solar mass black hole, and map out in real time any fluctuations in the gravitational potential around it, and maybe learn some more things about the structure of black holes.
Sure. Just take a moment. Well, let's wait for the specific.
Yeah.
Thank you.
I think I'm loud enough. So the mirror that's hanging there is not cooled. It's not in temperature control.
That's right. That's right.
So then, as a function of time, there's going to be a thermal expansion and then shrinking, and then you mentioned there's a quantum noise. Where's the quantum noise from? The room temperature shouldn't be all dominated by thermal effect?
Yes. It's a good question, which I could talk about for a long time. First off, there are changes in the temperature of the mass, and in particular induced by the fact that we're throwing currently several hundred megawatts of light power against it. It has an absorption of about 1/10 of a part per million. And so it's receiving something like a watt of power, and it's hanging in a vacuum. So of course it gets hot. Furthermore, because the thermal conductivity of fused silica is relatively low and has a fairly large coefficient of expansion with temperature, a mirror which starts out as a beautiful 4-kilometer long curve develops a bump which can defocus the system. So we have to apply additional heat in a donut form to compensate for that, to bring the mirror back to the correct form. Meanwhile, the mirror is heated up by a couple of degrees, maybe 10 degrees C or something like that. It is showing thermal noise, and that thermal noise scales with the square root of T. So you move from 300 to 310 Kelvin, which in the square root makes no practical difference in the level of the thermal noise. It's true, the thermal noise is something that has to do with the physical mass. The quantum noise is something that has to do with the photon sensing system that is bouncing off of it. So I hope that covered the yeah.
Okay, so last question. If you don't want to tell, that's fine. What's the coating material of the mirror?
It's tantalum pentoxide with silica as the second index. So that's a nice, it turns out that silica is a low loss material, even in the sputtered form, and has a reasonably high Q or low loss, more like Q of 10 to the 5 or something like that, if you will, or loss tangent 10 to the minus 5. The tantalum pentoxide is a messy material and has a loss more like 10 to the minus 3. And that's what really dominates the thermal noise. So we're looking for other formulations of two index systems which are lower, either intrinsically lower in their losses, or where we apply the tantalum pentoxide in other ways, either as micro-layers or through an annealing process where we heat the substrate before we put it down or while we're putting it down, and otherwise to try to drive it down. We're also looking at crystalline coatings, which can have potentially very low loss, but it's hard to make them bigger than something like this, and they may have some other problems as well. But it's a real knotty K-N-O-T-T-Y problem in material science, about which I know absolutely nothing.
So mentioned the Kagra, the Japanese experiment was trying to actually kill it.
Thank you. Yes, right. Right. So we operate currently at room temperature, and the Kagra experiment actually uses sapphire as its test mass material, has a very high thermal conductivity, so lower deformation under heating and so forth and so on, and also sapphire suspension wires, which are rather thicker than ours, because the way that they get heat out of the system is by conducting up those sapphire wires. They hold the external system at about 4 Kelvin, and they think they can maintain the test masses at about 10 Kelvin. And so there you've gone from 300 Kelvin to 10 Kelvin, square root of that, you've actually made a significant change in the thermal noise. So that's an approach. It's a pretty heavy-handed one. I'm sure that we'll all get to using cryogenic systems sometime in the future, but for now, we're going to be holding these things at room temperature. And it's an interesting point. I mean, the 40-kilometer dream machine that we talked about, the Cosmic Explorer, where I said you just use the same components to make it 10 times longer, we use that to convince ourselves and funding agencies that an investment of that kind would be well rewarded with the current technology. We definitely will also be pursuing cryogenics in parallel to drive that noise further down.
You mentioned funding for future observatories and how maybe it would have to be shifted away from, if you will, more standard observatories. And I'm wondering, just along those lines, is there a sign of people writing proposals at observatories that have to do with trying to be more responsive to, say, LIGO announcements?
I guess the simple answer is yes. And we see that in a number of different ways. We see a great deal of enthusiasm among observers for this new observing run. A lot of them are tailoring their observing time exploitation around the chance of being a participant in, say, another one of these neutron star observations. The other thing that we noted is that quite a number of the white papers that were submitted to the 2020 Astro Decadal just a couple of weeks ago stress how conventional astronomical systems are being proposed, either ground-based or space-based, to complement the gravitational wave data. And so it's clear that the astrophysics community is starting to eye this as an opportunity, and like any good drug dealer, we're delighted to see they're becoming dependent upon us, and they'll want more. And so it's a good sign that we're following through with our promise to do something which is beyond of curiosity, and I like GR, and I think it's really cool to either show once again that Einstein's predictions are right, or even more exciting, show that they were wrong. But we have to have a bigger base. And the binary neutron star proved to ourselves as well as to the larger community that really is true.
Hi. You spoke briefly about how as we get better instruments, you're going to be moving up towards larger masses combining. Is there any interest in going smaller and seeing smaller masses combine, or is it just we're looking at the bigger?
The problem is that as the masses get smaller, the signal gets smaller. And it also so happens that the interferometry that we currently know how to do it has poorer and poorer performance at higher frequencies. We've got a number of sketches on the blackboard of things that you could do if you could make mirrors with 10 times lower absorption loss. And I mean, the other kinds of problems that happen with, if you could turn up the laser power, you could improve the sensitivity in that regime. But there are all kinds of really weird things that happen besides, for instance, heating of the mirror and deformation of the mirror. There are also really significant torques applied to the mirror. If the beam is not exactly centered on the mirror, it twists the mirror away. When the system goes from not being in lock to the being in lock, it gets a huge kick. There are all these really strange dynamics that take place. We don't know how to handle much more power than we currently have. So it's hard to make a system that would be sensitive enough to see much smaller systems coming together. You also need them to come together at near relativistic speeds to get the kind of signal that you want. And once you take something as gluey and gummy and low mass as the sun, and you spin two normal functioning suns around each other, they smush. They don't get up to a high enough rate of rotation. A binary neutron star, it consists of two objects about the size of Providence or something like that, and they can get really close and at a really high velocity before they actually start to interact physically. And in that way, we get a large enough signal. So I think there isn't much hope, at least with the technologies we have in mind now, to see smaller objects. Also might be less interesting, I don't know.
Yeah. Are there any low-frequency electromagnetic noise which affect
Any low-frequency?
Electromagnetic waves?
Oh.
Interacting with the metallic piece of your detector?
Yes, and I guess it goes all the way down to DC. Charge on the test mass causes electrostatic attraction between the test masses and the surrounding cage, which is not as well seismically isolated, so it is a transfer function from there to the test masses. The entire thing is inside a Faraday cage, and so there aren't, in fact, EM waves of large amplitude that arrive, but we do have, one of the very important features of the observatories is to have a complete environmental monitoring system. So we have radio receivers of all different kinds, shapes, and sizes, microphones, seismometers, accelerometers, cosmic ray detectors, which are peppered throughout the system. We also have weather stations. It turns out that one of the biggest effects that we have difficulty dealing with is wind buffeting the building in which the system sits, causing tilts of the floor, which, despite our seismic isolation system, is coupled up and through. So anyway, we have trouble with electromagnetic coupling, and the way that we manage it is mostly through a Faraday cage, but then also monitoring. And with each one of our monitoring systems, we strive to have a monitor which is more sensitive than our interferometer to that particular disturbance. And in that way, we can reject signals that we see as coming from non-gravitational wave systems.
It's curious that you don't mention dark matter when talking about gravitational waves.
I think I've learned more about dark matter in my visit here today than I have in my previous lifetime. One person, I'm an instrument builder, not an astronomer or an astrophysicist or even a relativist. And one of the interesting things that was raised as a possibility, perhaps there are dark matter black holes. Is there any possibility that there would be a different signature, for instance, to a ring down or something like that, due to a dark matter black hole? It could be that we can shed some light on things. I think maybe the thing that I could see as the most direct and obvious way that we can contribute to these particular puzzles is to see a deviation from GR. And that could give an additional clue for constructing a theory which might help understand, well, the dark energy, dark matter problem. But it's not something that we think about as an experimental goal, and we don't see a recipe, at least a priori, to do something to our instruments or have a specific analysis regime that would allow us to pull that kind of information out better.
Sorry, do you have a follow-up? I'm so sorry.
Oh, it was just a question. What are the prospects for measuring polarization of the gravitational waves?
Oh, very, very good. And in fact, we already put some limits on deviations from Einstein's prediction of the spin 2 45-degree polarization vector with that first gravitational wave event that was measured in Virgo. Because while the two LIGO instruments, they were designed to be as parallel as possible to confirm detections, whereas what you really want to measure polarization is 2 at 45 degrees. Well, it turns out Virgo is over here somewhere and is at a cockamamie angle with respect to the 2 LIGO instruments. So as we now start to see detections in the 3 detectors, Virgo has really improved its sensitivity since last time by a factor of 3 or something like that. We'll be able to say more about the polarization, both as a tool to give more information about the angle of observation, but then also to test whether or not GR is working right. So we're on the path. Okay.
Now, this isn't the last of the questions, because we have out in the reception area, we have pizza for undergraduates, graduates who didn't manage to make the Q&A at lunchtime today, or somebody who has follow-up questions. So please do make use of that. I'm afraid you won't not off the hook yet.
Yeah, okay, that's good. As long as I have something for my throat, I'll be happy.
But no, please do, I'm sure you have many more questions. Let's ask them in that more informal, just in the